Okay, section 2.4. First thing we're going to talk about is conjugate acids and bases. Now, I'm just going to write out an equation here. Should be familiar. HCl, hydrogen chloride, hydrochloric acid, plus H2O, and that goes to H3O plus Cl minus. So this is in the form where the H plus ion is depicted as joining an H2O molecule, which is what happens in practice. So when we talk about conjugate acids and bases, it's helpful to depict the water molecules taking part in the reaction, which is what actually happens. Okay, so what are we talking about when we talk about a conjugate acid and a conjugate base? Well, let's take the most straightforward part of this. HCl is referred to as an acid, hydrochloric acid, so it's got the name acid in it. Now, it is not called an acid because it's got hydrogen in it, or, well, let's not talk about why it's not called an acid. It is called an acid because it's got the potential to donate this H plus ion, and it will donate this H plus ion to other things. So it's the fact that it's going to lose an H plus ion that makes it an acid. So that's what makes this an acid. Now, it follows that once it's already donated its H plus ion, it'll turn into a form of that molecule that lacks the H plus ion and is therefore a conjugate base. So if we look over on this side of the equation, we see the Cl minus ion, and that is an HCl molecule without the H. So once the molecule is given up its H plus, it turns into the conjugate base. With the H plus, it's an acid. Without it, it's a conjugate base. In this particular case, the Cl minus doesn't have any ability to take away the H plus from the H3O. In certain reversible reactions, it can do that in any reaction where it's going the other way. But nonetheless, it is a conjugate base to the HCl. Now, a little bit more confusingly, water is in the same position. For instance, the H2O molecule accepts the H plus ion and mops it up from the HCl molecule. So this H plus basically jumps over. That's the whole reaction, is the H plus jumping from one to the other. In that sense, the H2O is the conjugate base of the H3O plus molecule, which is the conjugate acid of the water molecule. So this one and this one are together as conjugate acid and base, and this one and this one are together as a conjugate acid and base. If that seemed a bit complicated, a very easy way of thinking of it is any molecule with an H is a conjugate acid of the same molecule without the H, which is its conjugate base. So if it loses an H on one side of the equation, then when it's lost the H, it's the H plus ion, it's a conjugate base. When it's got it, it's an acid, and that always holds true. It's a way of denoting which molecule is accepting a proton and which molecule is donating a proton on either side of the reaction. Alright, the next thing we're going to do is talk about neutralisation and a particular outcome of neutralisation. Neutralisation shouldn't be too new for you. It's just the idea of an acid plus a base creating a water and salt. Sorry, water and salt and heat. So here's the very most straightforward one. In this particular one, should be too new. The OH minus and the H plus both ionize out, and what we get is H2O plus NaCl. Sorry, I should point out that when they ionize out, they then react together and just go back to water to create water. It's the H2O. The Na and the Cl, we say they create NaCl. This is all happening in an aqueous environment, so NaCl is fully ionized, it's a salt, it's dissolved, and that is what happens, and heat. So that's neutralization. But you need to learn a very special case of what happens in a neutralization between particular acids and bases. Now we already know that there are strong acids and weak acids, and there are strong and weak bases as well. This example, the classic neutralization example, is only the most straightforward one. This is a strong acid here, hydrochloric acid, and sodium hydroxide is a strong base. So it's only one particular example. Something different happens when we react a strong acid with a weak base. So strong acid, weak base, or alternatively when we react a strong base with a weak acid. So let's look at one example of that now to show what happens. So I'll give the example of that's in the textbook, which is hydrochloric acid plus ammonia. So that's ammonia, which is NH3, not to be confused with ammonium, which is NH4, which has a very, very different property in acid-base reactions, so it's important to know the distinction of that. Alright. So, the issue here is that hydrochloric acid, as we know, is a strong acid, but ammonia is only a weak base. It's a weak base, which we perhaps should go back over. A weak base is a base that creates OH minus ions when you put it in water. So it's a substance that will create OH minus ions when you put it in water, or it will absorb H plus ions. But it does not fully dissociate when you put it in water. Just like with a strong acid, weak acid case, it will only partially dissociate, which means it'll have an equilibrium type reaction going on. So the ammonia base reaction, we'll clear that up first before we talk about what happens when we react it. The ammonia base reaction is if you put NH3 into H2O, it'll combine in a reverse fashion, and what will happen is NH3 will, it absorbs an H plus ion from the water, and creates a hydroxide ion. So that's a pretty standard weak base formula. In fact, it's be well placed to know it, because you may well be asked to describe a weak base reaction, and this is the classic one. So ammonia, NH3 minus plus H2O goes to NH4 plus OH minus. That's an equilibrium reaction. It's got a forward and a back. That's the fact that it's equilibrium. It's not fully dissociating. or well, it's not even really dissociating it, but it's not fully reacting with water to create the OH minus, is what means that it's a weak acid. So that's the weak, a weak acid, a weak base. It's a weak base. It's creating OH minus. So that's that part of it. The question is, what happens when we neutralize a weak base with a strong acid? A strong acid with a weak base. Let's talk about that. So on the one hand, you get a similar thing to what you might expect from a standard neutralization reaction. Here we'll go HCl plus NH3 and goes to ammonium chloride salt plus heat. Not water in this case because of the nature of the base question, but the two compounds react, they release heat. This is a salt. It's pretty standard. By the way, this is just a one-way reaction. Never mind the fact that this is a weak acid, weak base rather. Let's not say that. It's a weak base. The strong acid reacts with it. Reacts with it completely and irreversibly, and we get this compound. But this compound is not a neutral salt. When we react a strong acid with a weak base, strong acid plus weak base, the salt we get is acidic. It's a slightly acidic salt. And if it's a weak acid and a strong base, we get a slightly basic salt. Let's look at the chemistry of that now. This NH4Cl dissociates partially actually no, completely. So dissociates into NH4 plus Cl, and NH4 then acts as a weak acid. So then plus H2O here goes to H3O plus H3 minus. Now you do well to know this NH4 plus H2O equation as well. It comes up a bit. So NH4 plus H2O goes to H3O plus NH3 minus, and of course that can be reversed around as well. Okay, the next thing we're going to talk about is jumping ahead within this dot point a bit down to buffers. Come back to something else that's next chronologically, but not as linked in terms of the concept. So we'll talk about buffers now and what's going on there. And it all comes down to equilibrium. Alright, buffers. Now, the equation we're going to look at is set out slightly differently in the textbook, but because it makes more sense in the format that we've already looked at it in the CO2 reaction, I'm going to state it slightly differently. The principle is identical and the reaction is the same. You might be asked, it's a dot point that you might be asked to explain the action of a buffer in a natural system. You should understand what a buffer is anyway and how it works in general. but I'll give you an example that holds true for a natural system. The natural system is our blood. Our blood has dissolved carbon dioxide in it, and as such has this compound H2CO3. Now H2CO3, when it is water, goes through a reversible reaction creating H plus and HCO3 minus, and as such we can see that it is a weak acid. It is acidic because it gives up an H plus ion, and it is an acid. It is acidic because it's an H plus ion, and it's weak because it's a reversible reaction. Now, whenever there is a weak acid or a weak base in a system, it will work as a buffer, and this is why. Let us imagine that we increase the H plus concentration. So we add another substance. Let's say we add some hydrogen chloride. It'd be a bad situation if somebody added hydrochloric acid to your blood, but let's imagine maybe even just a small amount is added, and now what's that going to do? That's going to increase the H plus concentration of the substance. Now let's have a look what would happen in a system with a whole lot of this weak acid in it if we increase the H plus concentration. Well, if we increase the H plus concentration, that's going to mean that there's more H pluses running around, which means it's more likely that one of them will bang into an HCO3 minus ion, which means that in general there's going to be more interactions between these two, which means more of the back reaction. So the back reaction is going to speed up, which means we'll get more of this and less of both of these. So if we increase the H plus concentration, and there's already a weak acid in there, more of that weak acid is going to reassociate, and we're going to get a drop in the amount of it that's contributing to H plus. So in response to increasing the H plus, the response of this weak acid reaction is to decrease the H plus. So just as we might imagine with Le Chatelier's principle, it is going to move against the change in pH. It's going to move against rather the disturbance of the equilibrium, and therefore it's going to move against any change in pH, or H plus concentration rather, which is the same thing. So if we increase the H plus concentration, what this reaction will do is mitigate to some extent. It won't remove the effect, but it will mitigate the effect. So it'll slow down and attempt to change the pH by adding H plus. Alright, that's pretty straightforward, but let's imagine now that we, instead of doing this, instead of adding HCl, let's just write this reaction out again. So H2CO3 plus, plus goes to H plus plus HCO minus. Okay. So let's now imagine, so we've already seen that if we try to increase the H plus concentration, this reaction will react against that and mitigate the effect. Let's see what happens now if we add something like, let's say, potassium hydroxide. So potassium hydroxide is a strong base. It's going to create potassium ions and hydroxide ions. Now, what that's going to do, as we know, is that the OH ions are going to react with any H plus ions, but not with any of them, but with some of them. The net effect of that is going to be, we add a base, of course, that's going to reduce the H plus concentration. So some of these H pluses are going to get absorbed. There's going to be an initial move downwards. Now, remembering, of course, that it's a weak acid situation. Now, if we reduce the number of H plus ions from this equilibrium system, what's going to happen? Well, once again, the system is going to react against that change. In this particular case, there's less H plus flying around, which means there's less H plus to interact with HCO3, which means there's less reactions going back. So that's going to drop, but there's the same number going forward, which means that this is going to increase and this is going to increase in reaction. So once again, to graph it out, let's imagine there was initial equilibrium concentration that was flat. So the concentration of H plus was flat at some level over time, and then bang, we've added OH minus, added the potassium hydroxide, which turns into OH minus. What that's going to do is that's going to drop the H plus level down, and then it's going to come back again and increase a little and then level off at a lower level. It's going to be a gap here. But an initial drop is going to be mitigated against by Le Chatelier's principle. It's not going to go back up to the same level. It's going to be mitigated against and level out lower than it was before, but not as low as it was originally, because this equilibrium reaction is going to react against it. And so what we've just described is a weak acid acting against an increase in H plus and a decrease. So it doesn't matter that it's a weak acid. If it's at an equilibrium point, it's going to react against both directions. And the same goes for a weak base. If the weak base is at equilibrium, any change in H plus is going to change that equilibrium reaction, and then Le Chatelier's principle is going to kick in, and we're going to see that change mitigated against. So once again, on a graph, should try to keep this straight. Why don't we just go to on a graph of time versus, let's draw it out straight line. So time down here, H plus concentration over here, and let's even imagine that we just add H2CO3 to begin with. Let's go through it. So if we just add H2CO3, first thing that's going to happen is it's going to go very quickly. A lot of H plus is going to be formed, and then it's going to level off over time. Let's say that the next thing we do is add a bunch of H plus in the form of HCl at this point. Well, that's going to jump that level up, but then it's going to taper down again to a new level. And let's say we added instead, actually at the same point, let's not, if we came along later, because if we added potassium hydroxide at that point, the opposite's going to happen. It's going to drop down, and then it's going to come up and level out again. So that is the effect. So this is, if we added hydroxide, this is if we added H plus. And of course it needs to be at equilibrium beforehand. But we can see in both cases, the buffer, the weak acid buffer, so this is in the reaction, H2CO3 goes reversibly, of course, H plus plus HCO3 minus. In both cases, the presence of this weak acid, it could be a weak base as well, it works exactly the same way, is to the fact that it's there, it's mitigated a change. It's come back again because that buffer is there. And that's the role of buffers in natural systems. It's to make sure that the pH doesn't change too rapidly or too far. It helps to lock the pH within an acceptable range that biological reactions that need to occur can occur at. So that's buffers. Now, the final thing I'm going to talk about is in section 2.4, it's quite separate to the others, the effect, rather the equation. It's quite a quick one. It's a titration equation that you'll need to know. It's very simply V1C1 equals V2 C2, and you'll always be given 3 of these. Now, what do they stand for? V1 is the volume of the first thing, so either the acid or the base. Just to be absolutely clear, we're talking about titration. We're reacting a certain amount of a certain concentration of acid against a certain amount, a certain concentration of base, and when they're neutral, this is when they're neutral. So if it's perfectly neutralized, this is when this equation is relevant. So the volume of the acid, say, multiplied by the concentration of the acid, it's going to be equal to the volume of the base multiplied by the concentration of the base. And of course, they'll always give you 3 of these, and you'll just need to find the 4th one by applying this formula. So if you only got 2 of them, you can't find anything. They'll always give you 3 and ask you to find the 4th, and it's very straightforward maths. But such a useful equation that I thought it warranted a special mention. Alright, that's all for 2.4.